Hey guys, today we are going to complete what I call Vectors 101. This note packet is just going to go through all of the concepts that we have covered in 6.3 and 6.4. There is no assignment today. It is just to make sure that you are understanding everything that we've covered so far on vectors. Okay, so number one, I'm going to have you go ahead and draw a directed line segment. But we are going to be doing some calculations with our directed line segment. So we're going to have our initial point A at 0, 0, and our terminal point B at 3, 5. So go ahead and graph that. So I need to be able to go to the right 3, up 1, 2, 3, 4, 5. That's where B would be. This is where A would be. Okay, so when you have a directed line segment, you have an initial point, where are you starting? A terminal point, where are you ending? And when you connect them, it's important that you show what direction you were traveling. So this, my friends, is a directed line segment. It's a segment because it does stop, but it's directed because you know the path that you took to get from the initial point to the terminal point. Name the directed line segment. Now, when you name them, you always use the letter of the initial point first and the terminal point second. So I started at A, ended at B, so it's AB. Then it's similar to how you label a ray in geometry, but because it is technically a segment, you don't show the full arrow, it's just half of the arrow. In order for something to be a directed line segment, you need two things. You need what's called magnitude, and magnitude is the length. In order to find that, we use the distance formula. The other thing that you need is called direction, and the direction is the slope. So this directed line segment has to have a given length, and it has to have a slope of some sort. So let's go ahead. It says determine those two elements for your directed line segment. So if I want to find the magnitude is length. So we are going to go ahead and use the distance formula. So I am going from 0, 0 to 3, 5. When you are doing the distance formula, it's second x minus first x. So 3 minus 0 is 3, quantity squared, plus the second y minus the first y. 5 minus 0 is 5, quantity squared. 3 squared has a value of 9. 5 squared has a value of 25. 9 plus 25 is 34. I cannot break apart a 34 because it's created from 2 times 17. So the square root of 34 is the magnitude for directed line segment AB. If I want to find the direction is the slope. So it's the second y minus the first y, so 5 minus 0, over the second x minus the first x. So 3 minus 0. 5 minus 0 is 5. 3 minus 0 is 3. So your direction is 5/3. You go up 5 over 3, up 5 over 3, and that's how you could continue that directed line segment if you so choose to. So this was the very first idea. What is a directed line segment? How do you name it? What are the two components that you need in order to have a directed line segment? And then how do you find those two components? Then we talked about some other really cool things. The set of all directed line segments that are equivalent. What equivalent means is they have the same magnitude and same direction. Okay, so they are the same length, and in a sense they're parallel. They will never cross, okay? So the set of all directed line segments that are equivalent to a given directed line segment is a vector. That's what a vector is. It's a set of any directed line segments that would have the same length and be parallel to a given line segment or a directed line segment. How do you denote a vector? You know something is a vector if it is shown as a lowercase value that is also bold print. So like lowercase v bolded, W, often they will use U. So you know that they're talking about a vector if the letter is lowercase and the letters are bold. If a vector v is said to be in standard position, what do you know about it? Well, think about when we graphed standard angles or angles in standard position. Remember, the vertex of the angle had to be at 0, 0. So it is definitely related to that. In order for a vector to be in standard position, its initial point, so where it starts, its initial point is at 0, 0. So standard position really means that you are utilizing that origin of the coordinate plane. When a vector is in standard position, so its initial point is at 0, 0, and then the terminal point can be anywhere, you can represent the vector in component form. Now, component form, remember, that's where you have your triangular edges, okay? Find the component form and the magnitude of vector v if it has the initial point, so it's starting at 4, -7, and it's ending at -1, 5. So what they're saying is, like, what would be your component form if you took this vector and you moved it on a coordinate plane, so that way instead of starting at 4, -7, it would now be starting at 0, 0, okay? In order to find the component form, you take the second x minus the first x, so -1 minus 4. Then you take the second y minus the first y, 5 minus a -7. So your component form, -1 minus 4 more is a -5. 5 minus a -7, if you minus a negative, you're actually adding. 5 plus 7 is 12. That is the component form. So if I took this directed line segment and I moved it so that way the initial point was at 0, 0, the terminal point would fall at -5, 12. Then those two directed line segments would have the same length and they would have the same direction. That's what that means. Okay, now if I want to find the magnitude, they taught us a shortcut. They said if you have component form, in order to find the magnitude, the length, you can take the x value of the component form, because if you look, it's already part of the distance formula. It's the second x minus the first x. Now you just have to square that. So -5 squared is 25. Plus, same thing here, you take the y value and you square it, because this was the second y minus the first y. We got a 12. Now you square it to get to 144. Add those two together. 25 plus 144 is 169. The square root of 169 is 13. So the component form, if you move it so the initial point is at 0, 0, the terminal point will be at -5, 12. The length of that vector, the magnitude is 13. Okay, what are 3 main vector operations we've covered? We've covered addition. Remember, addition does include subtraction because subtraction is technically adding the opposite. Okay, we did a scalar multiplication. That's where you are distributing. Then we just learned what's called a dot product. So we did addition, which includes subtraction, scalar multiplication, and dot products. So if they give us these 3 vectors, and I know they're vectors because they're lowercase and they are bolded, can we find the following? So they want us to take u, -1, 3, and add it to v, -2, 4. When you are adding or subtracting, you add the x values together and the y values together. So here the x value is -1, and here in my second vector the x value is -2. -1 plus -2 makes -3. Now I have to add the y components. 3 plus 4 is 7. Done. Now this is scalar multiplying. So 3 is outside of vector w, which is 1 and -2. If you have a scalar, you just go ahead and distribute. 1 times 3 is 3. 3 times a -2 is a -6. There's an example of scalar multiplication. Now dot product. I'm going to go ahead and write this just so I can make sure that I point out the correct values. Okay, dot product. Your solution will be one single number instead of an actual vector in component form. Remember, you multiply the x values together. So it's -2 times 1 plus, then you multiply the y values together. 4 times -2. Well, negative 2 times 1 is negative 2, plus 4 times negative 2 is negative 8. Negative 2 plus negative 8 is negative 10. So there's an example of the 3 main vector operations that we covered in 6.3 and 6.4. And let's keep going on Vector 101. So now we're going to go ahead and combine those different things. This is a dot product, but they want us to do a scalar multiplication, take 2 into vector v. So I'm keeping u the same, negative 1 and 3. I'm finding the dot product, but I want to take 2 times v. So negative 2 times 2 is negative 4. 2 times 4 is 8. Now when I find the dot product, multiply the x's together. Negative 1 times negative 4 is 4. Plus, multiply the y's together. 3 times 8 is 24. 4 plus 24 is 28. The next one is adding, but there's a scalar in here. We want to take vector v, negative 2, 4, and add it to vector w after you have distributed in a 2. Remember, order of operations, you would multiply by 2 before you would add. So if I take w and I need to multiply a 2 into both terms. So 1 times 2 is 2. 2 times negative 2 is negative 4. Now I will add them. Negative 2 plus 2 is 0. 4 plus negative 4 is 0. So remember, this is a 0 vector. It means its initial point starts and your terminal point is on the exact same spot. So it is just a point. Last, when I am looking at something like this, order of operations, you always do what's in parentheses first. So I need to find the dot product between u, which is negative 1 and 3, and v, which is negative 2 and 4. So I multiply the x's together. Negative 1 times negative 2, that's a 2. Plus 3 times 4, that's a 12. 2 plus 12 is 14. So this right here has a value of 14. I still have to multiply by w, and w is a vector in component form. So now I'm going to go ahead and distribute the 14. 14 times 1 is 14. 14 times negative 2 is negative 28. So one thing to notice is when you are doing vector operations, there are times where your solution will be a component form of a vector. There are times where your solution may be just a single number because you are doing dot products. Okay, next part. Now a unit vector. So cool, you guys. This is when everything tied in together with our unit circle. A unit vector, what that means is that your magnitude or the length equals 1. So if you were to graph it on a coordinate plane, it actually lines up perfectly with the unit circle. So cool. Now the formula, in order to take any vector in component form and convert it to what's called a unit vector, the formula was this. You take your vector in component form over the magnitude. So remember, you can take your first component squared plus your second component squared. This is how you can turn any vector into a unit vector. So they're giving us vector negative 2, 5. They want us to turn it into a unit vector and then basically verify or prove that it really has a magnitude of 1. So let's go ahead and do this. The top is your component form, negative 2, 5. Now the bottom, we have to find the magnitude. We find that by squaring the first value of our component form. Negative 2 squared is 4. Plus, now you square the second value. 5 squared is 25. So I have negative 2, 5 on the top. 4 plus 25 is 29. I cannot break that down. Now what they had us do when we were talking about unit vectors is they said in order to turn this into a scalar, they bring out 1 over the magnitude, so that way it is next to the component form. Okay, so that's what you'd want to do next. Now, in order to actually find your unit vector, you go ahead and do scalar multiplication. So it kind of all ties together. Keep in mind that negative 2 and 5 are technically fractions as well. They have a denominator of 1. So that way when I go ahead and multiply that in, I can do top times top, bottom times bottom. What I would have is negative 2 over the square root of 29. and positive 5 over the square root of 29. Now, because one of our solutions is to find a unit vector, this is technically a solution. You never want a square root in the bottom of a final solution. So I do need to go ahead and rationalize the denominator, and this goes for both fractions. So I will be multiplying both top and bottom by the square root of 29. So my unit vector is negative 2 times the square root of 29 over square root of 29 times the square root of 29 is 29. This is 5 times the square root of 29 over square root of 29 times the square root of 29 is 29. That is your unit vector. Now what they want you to do is to prove it. You have to show that it really has a magnitude of 1. So you have underneath the radical the first value from the component form, so negative 2 square root of 29 over 29 squared, plus the second value, 5 times the square root of 29 over 29 squared. Now here, this is properties of exponents. You have to remember that this exponent goes to everything on the top and everything on the bottom. Negative 2 squared, this is a 4. If you square a square root, the square root symbol cancels, but it does not change what's underneath, so it's a 29. 29 squared, 29 times 29 is 841, plus 5 squared is 25. If you square a square root, the symbol cancels, but it does not change what's underneath. 29 squared is 841. Now I'm going to go ahead and multiply. 4 times 29 is 116 over 841. 25 times 29 is 725 over 841. I can combine these because I have a common denominator. 116 plus 725, you guys, that's 841. And 841 over 841 is 1, and the square root of 1 is 1. So this is my unit vector. We proved that by finding the magnitude, and the magnitude did equal 1, which is what the definition of a unit vector is. Awesome. Moving on. Then what happened is they added in I and j. Remember, I represents the x or the horizontal value in a component form of a vector. J represents the y or the vertical value. When you write your solution using I and j, what that's called is a linear combination. So it does not change the value at all. It's just an alternate way of writing your solution. Again, that's called a linear combination. So this says let vector u be a vector with an initial point, so it's starting at 2, negative 5. Terminal point, it's ending at negative 1, 3. Write it in component form and then as a linear combination. So if I am doing component form, remember, it's the second x minus the first x, so negative 1 minus 2. Then it's the second y minus the first y, so 3 minus a negative 5. So your component form, negative 1 minus 2 more is negative 3. Minus a negative changes to a plus. 3 plus 5 is 8. So this is the component form. If I want to write it as a linear combination, negative 3 is the x value, so you show that by having it connected to an I. The 8 is positive, so it's plus. The 8 is the y value, so you show that by connecting it to the letter j. These two things mean the exact same thing. This is the component form. This is the linear combination. Okay? It says, guess what? We can perform vector operations if a vector is represented as a linear combination too. So again, what I think is the easiest is to first convert from linear combination to component form. So what I would do is say, okay, vector u, the x value, so the first value of my component form would be negative 3. Then my second value is a positive 8. For v, it is 2 and negative 1. So the first thing I do is go from linear combination into that component form. Then I can go ahead and do this. So I want to take u and multiply each component, each value in that vector by 2. So negative 3 times 2 is negative 6. 8 times 2 is 16. Then they want us to add it to vector v if you've distributed in a 3. 2 times 3 is 6. Negative 1 times 3 is negative 3. So now I add them together using vector addition. Negative 6 plus 6 is 0. 16 plus a negative 3 is 13. So that is your component form. Or you could say 0i plus 13j. Or because this is a 0, you can simply just say 13j. All three of these notations mean the same thing. If you have a 0 in your linear combination form, it is okay to eliminate that. So you could write it as 0i plus 13j, or just completely eliminate the 0 and keep it as 13j. Moving on, guys. Back to the idea of the unit vector and why it's so cool. If u is a unit vector, that means that the angle, if you are graphing counterclockwise from the positive x-axis, so you have to have one, if you're picturing it as an angle, you have to have one of those rays on the x-axis pointing to the right. Okay, the terminal point u lies on the unit circle. So it took us all the way back to our first chapter of trig. Kind of cool. Now we can find the direction angle for vectors. Direction angle, what's very important here is that you know what quadrant you're looking at. Remember, the first value is the x, the second value is the y. So here, the x is the cosine. So the cosine is positive because my first value is positive. The sine is positive because the second value is positive. Okay, now if you're thinking of your coordinate plane, your cosine and your sine are both positive in quadrant 1. So when I find my answer, when I find that unit vector, it says it's starting from the x-axis going the positive direction. My direction angle is this measurement right here. The formula for that is the tangent of theta equals b over a. So it's 3 over 3. So the tangent of theta equals 1. In order to solve for theta, you have to do the inverse tangent. The inverse tangent of 1 is what would equal theta, because in order to move a tangent, you have to do the inverse. Now make sure your calculator is in degree mode. The inverse tangent of 1 equals 45 degrees. Now 45 degrees is in quadrant 1, and that's where we needed it to be, so we're done. Okay, the next one. The cosine, the x value is positive, so we know we're going to the right. The sine is negative. So if I go to the right and down, we are in quadrant 4. So when I'm finding my direction angle, it means I'm starting here and going all the way around here. So I know this thing's going to be more than 270 degrees because it's passing the 90, passing the 180, passing the 270. Okay, let's go ahead and find the formula. Tangent of theta equals b over a, negative 4 over 3. In order to solve for theta, you need to take the inverse tangent of each side. So theta equals the inverse tangent of negative 4 divided by 3. When you put that in your calculator, and again, please make sure that you are in degree mode, you would get negative 53.13 degrees. So what this measurement is if you travel downwards to where your terminal point ended. This measurement right here is 53.13. That's that reference angle like we talked about during the year. We want our direction angle, meaning we want this whole piece. A full circle is 360. So if I minus the 53.13, it will tell me how much I traveled from where I started on the x-axis to where that terminal point would be. 360 degrees minus 53.13 is 306.87 degrees. Again, we said that we would have to have more than 270. That is more than 270. It is in quadrant 4. We are good to go. Last page. This is why you're not getting notes today, you guys. Okay, here's another idea. If you have two vectors and they are in standard position, meaning they both have their initial point at 0, 0. Okay, so like this could be vector u and this could be vector v. You can find the angle that is between them using this formula. You find the dot product on the top, you multiply by the two magnitudes on the bottom. And that is all equal to the cosine of theta. So the cosine of theta is equal to the dot product of the two vectors, and then you multiply by the magnitudes. So the first thing that I like to do, if you remember from the notes, I like to go ahead and find those magnitudes first. So if I'm finding the magnitude of vector u, I can take the x value and square it. 3 squared is 9. Plus the y value and square it. Negative 2 squared is 4. So the magnitude, 9 plus 4 is 13. I can't simplify that. Now if I'm finding the magnitude of vector v, if I take 1 squared, it's 1, plus 5 squared is 25. 1 plus 25 is 26. Again, I can't simplify that because this would be 2 times 13. Now I find the dot product. So I multiply the two x's together. 3 times 1 is 3, plus multiply the two y's together. Negative 2 times 5 is negative 10. 3 plus a negative 10 is negative 7. So here's my formula. The cosine of theta equals negative 7 over, if you multiply those two, 13 times 26 is the square root of 338. I can break that apart because this is 13 times 26. I know that because that's what I used to create it, but 26 is 13 times 2. So I can go ahead and take the right side. I can cross off 2 13, so it's 13 over the square root of 2. So my formula for this, after I simplified, it's the cosine of theta equals negative 7 over 13 square roots of 2. What I want to do is solve for theta. So I need to take the inverse cosine. So theta equals the inverse cosine. It's going to open a parenthesis. The top is a negative 7 divided by. Now here's another scenario like we had in the notes where you're going to have 13 square roots of 2 in its own set of parentheses. So that way it calculates this value before you do the division. When you put this in your calculator, inverse cosine, it will open a parenthesis, negative 7 divided by, open a parenthesis, 13 times the square root of 2, close it, you would get 112.38 degrees. And again, the angle between two vectors has to fall somewhere between 0 and 180. This does, so we're good to go. Let's do one more because this is kind of a lengthy problem, and it's kind of a longer process. I find the magnitudes first. So the magnitude for vector u, if I take the x value and square it, negative 2 squared is 4. If I take the y value and square it, 4 squared is 16. 4 plus 16 is 20. I can break that down. 4 times 5. The 4 is 2 times 2. So the magnitude of vector u, because I can cross off two 2's, I can write one outside, it's 2 square roots of 5. Now if I find the magnitude for vector v, you take the first value and square it, 3 squared is 9. The second value and square it, 1 squared is 1. 9 plus 1 is 10. I cannot simplify that because 10 is created from 2 times 5, so I would not have any pairs to take out. Okay, now to find the dot product, because that's what the numerator is. You multiply the x's together, negative 6. Plus, you multiply the y's together, 4. So it's negative 2. So I have the two magnitudes, and I have the dot product. So I'm ready to go. I have the cosine of theta equals the dot product goes on the top. Now on the bottom, you go ahead and outside numbers get multiplied with outside, inside get multiplied with inside. So the 2 is on the outside. 10 times 5 is 50. The first thing I notice is I can go ahead and cross that off. So I can simplify this side by saying negative 1 over the square root of 50. Now, yes, we can simplify this, but now thinking about it, it's going to be easier in your calculator to just put it in this way because this is not your final answer, so you don't necessarily have to worry about simplifying it. If I want theta by itself, I would take the inverse cosine to move it over here, it will open a parenthesis, -1 divided by the square root of 50. When you plug that in your calculator, again, make sure that it is in degree mode. You should find that it's 98.13 degrees. So again, it's between 0 and 90. Now here is the last idea from 6.4, okay? It's a new idea. They can take this formula and we're gonna go ahead and see how this works, okay? So if I have this formula, the formula to find the angle between two vectors, we can actually rewrite this so that way it's set equal to the dot product. What you'd have to do is multiply both sides by the denominator. So if I multiply this over here, it's just a lot of little lines. There we go. So by multiplying, this would cancel. So your dot product would equal the magnitude of vector u times the magnitude of vector v times the cosine of theta. This is equivalent to this, and that's what I was going to have you put right here, but I thought it was just a little bit better to show you how it works this way. Okay, so they took this idea, this was the formula to find the angle between two vectors that both start at 0, 0. By just rewriting this in a different way, you can see that the dot product is equal to the magnitude of vector u, the magnitude of vector v times the cosine of theta. This produces an alternate way to calculate dot product because that's what it's equal to. From this form, we can look into something called orthogonal. So another fun word, orthogonal vectors. Okay, the terms orthogonal and perpendicular, they mean the same thing. It means that you have a right angle. So what they're doing is just expanding your vocabulary rather than saying, hey, these two vectors are perpendicular, meaning that they form a right angle. They're calling them orthogonal. Kind of cool, but that's all that it means. In order to see if two vectors are orthogonal or perpendicular, the dot product must equal 0. So if you find a dot product and it equals 0, what that means is that the two vectors are orthogonal, meaning they are perpendicular, so they create a right angle. So this is as far as you'd have to go with this. So we're going to go ahead. If they give you two vectors, can you figure out if they're orthogonal? What that means is you find the dot product and see if it's equal to 0. If it's equal to 0, yes, they are. If it's not, then no, they're not. So if I am finding the dot product, multiply the x's. 2 times 6 is 12. Plus, multiply the y's. -3 times 4 is -12. Positive 12 plus a -12 is 0. The dot product is 0, so yes, they are orthogonal. That's all that means, and now we have officially finished 6.4. Again, no assignment today. I just wanted you to have one more chance to look at vectors on our last week of College Trig. Have a great rest of your day. Talk to you soon.